All right, so we have the radius and the interval of convergence. So what this is it gives us a set number of x's, or it gives us an interval of x values that we can substitute into our series that make a good approximation of our function. So I can't always plug in a value for x and get a good approximation. There are only for some functions or for some series, there are only certain values of x that you are allowed to plug in. And this is where, and they will be located in the interval of convergence. Okay. The radius of convergence tells us how far the tells us how far away from center you can be from your center and still have a good approximation. So there are three outcomes that you can get when calculating your interval of convergence. The first is if you, if only the C value is a good approximation. So sometimes that happens, only the value that we're centered around is a good approximation, okay? Another situation that can happen is that you end up with an interval of convergence. So the value always C is in that interval, and then it's what is the distance, the positive distance radius from C and the negative radius from C, and that makes your interval of convergence. What we have to do, we're not sure about the endpoint, so we'll have to test them to see if they converge or not. The last thing that can happen is that you can plug in any value for X, and your series is a good approximation. Okay? What we do is we use the ratio test for our radius of convergence. And just so you remember, we're looking at when the sum of the series converges is when the limit of the absolute value of the next term over the current term is less than 1. Okay? So let's do one. So we're going to find the radius and the interval of convergence for each. So I'm looking at this problem, and we have, it's not a geometric series. That's the first thing I want to look for. And so I'm going to have to look to see, I'm going to apply the ratio test to see what our radius and our interval of convergence are. So I have n plus 1 factorial times x to the n plus 1 all over 1 times the reciprocal, so 1 over n factorial times x to the n. And what we want is that for this value to be, this limit to be less than 1, because when it's less than 1, the series converges. Okay, so we're going to do some simplifying. I have n factorial can be rewritten as n plus 1 times n factorial, and then x to the n can be rewritten, or x to the n plus 1 can be rewritten as x to the n times x to the 1, and then I'm going to put this all over n factorial x to the n, and that has to be less than 1. So I notice that these cancel, leaving me with the limit as n approaches infinity of the absolute value of n plus 1 times infinity, times x. And what we want is for the limit to be less than 1. Okay, so when I substitute in infinity plus 1 is just infinity, times x. So I get the absolute value of infinity times x. And the goal is to make that less than 1. So what values of x are we going to have that make this this inequality true? And it is when this is only true when x is equal to 0. But then as soon as x is equal to 1, 2, 3, even 1/2, we're infinity times 1/2 is still going to be infinity. It's still going to be greater than 1. Okay, so we know that this is only true when x is equal to 0. So that means that the radius is equal to 0. And my interval of convergence is x is equal to 0. Really, it's not a interval, it's a point of convergence because it's the only that's the only place where the series is going to converge, is where our C value is. I know that my C value, because my series is set up as x minus 0, my C value would be 0. So the point of convergence is that C is equal to 0. All right. Next up, let's go ahead and tackle number 2. So we have the sum from n equals 0 to infinity of -1 to the n times x to the 2n plus 1 over 2n plus 1. Again, not a geometric series. So let's go ahead and think about what value are we centered around first off. And looking at the x term, I can see that, again, this is x minus 0. So my C value is x is equal to 0. Or my C is equal to 0. Okay, so I have the limit as n approaches infinity of the absolute value of x to the, I'm not going to do the -1 since the absolute value is going to take care of that. So I have 2 times n plus 1 over 2 times n plus 1 factorial times the reciprocal of a sub n, which is 2n plus 1 factorial over x to the 2n plus 1. Let's do some simplifying. So I have the limit. Oh, and again, we want this limit to be less than 1. So I'm going to add that in right there. The limit as n approaches infinity of x to the 2n plus 2 plus 1 is 3 over, this is going to be the same, 2n plus 3 factorial times 2n plus 1 factorial all over x to the 2n plus 1. And that needs to be less than 1. Okay, the limit as n approaches infinity. If you can skip this step, that's fine. Okay, but I can see that I'm trying to cancel this 2n plus 1. So I can rewrite this as x to the 2n, right? And it's adding, since I'm adding exponents, the bases are being multiplied, so I get x times x to the 3 over over 2n plus 1 factorial, since I want to try and cancel out this term. But then I need to make sure I multiply by the factors of 2n plus 2 and 2n plus 3. So the next two factors in my factorial. And then I get x in the denominator, x to the 2n times x to the 1, since the exponents are being added. And then in the numerator, I have this 2n factorial, 2n plus 1 factorial, and then we want that to be less than 1. Okay, we have a lot of canceling to do, so 2n plus 1 factorials cancel. X to the 2n and x to the 2n cancel. And then it looks like x, and then I can change this to x squared. All right, so I have the limit as n approaches infinity of the absolute value of x squared over 2n plus 2 times 2n plus 3, and we want that to be less than 1. All right, we're plugging in, we're going to substitute in infinity for n, so that is only right here. We leave the x alone because that is not being substituted. because it's the limit as n goes to infinity. So when I divide by infinity, basically I get x squared over infinity has to be less than 1. And anything divided by infinity is going to equal 0. This is a Bobo-Bot meets DC issue. The denominator is just growing so much faster than the numerator. So we end up with 0 is less than 1. And this is always true. That means that for all values of x, this is going to be true. So by ratio test, the series converges for all values of x. Therefore, the radius of convergence is r is equal to infinity. Okay, so the radius is equal to infinity, and the interval of convergence would be negative infinity to infinity. So basically we can substitute any value of x into our polynomial, into our series, and it will make a good approximation for that value. Okay. Let's go ahead and look at number 3. So the sum from n equals 0 to infinity of negative 1 to the n plus 1 times x minus 2 to the n, and all over n times 2n squared. So looking at the x term, I can see that this is x minus 2, so the c value, we're going to be centered around x equals 2, or c is equal to 2. Okay. Next up, let's go ahead and apply the ratio test. So I have the limit as n approaches infinity of the absolute value of x minus 2 to the n plus 1 over n plus 1 times 2 to the n plus 1. So raising the power by 1, or we're looking at the next term. So the a sub n term would, I'm going to take the reciprocal of a sub n, which is n times 2 to the n times x minus 2 to the n. All right. And this has to be, because we're looking for where it converges, this limit has to be less than 1. Okay. All right. Let's go ahead and, again, if you can skip this step, that's fine. The limit as n approaches infinity of x minus 2 to the n times x minus 2 to the 1 all over n plus 1 times 2 to the n times 2, since the exponents are being added. Okay, this one can stay. N times 2 to the n all over, or over x minus 2 to the n, and that limit has to be less than 1. Okay, canceling, we get those cancel, and the 2 to the n's cancel, and I think that's it. So we have the limit as n approaches infinity of x minus 2 times n times 2 times n plus 2. And again, this has to be less than 1. All right, so when I substitute in my infinity, okay, so there's 2 ways we can do this. When I substitute in my infinity, I see that I'm going to get infinity over infinity, so I can apply L'Hopital. I can also see that these terms, we have a each DC situation, so these terms are going to cancel, which is going to give me x minus 2. But let's go ahead and use L'Hopital. So I'm going to substitute in my infinity. I get infinity over infinity is less than 1. So I can apply L'Hopital. So I have the limit as n approaches infinity, And the derivative of n is 1, so I get x minus 2. The derivative of n plus 2 is 1, so I get over 2. Same thing as if I had just, as I, well, okay, now I can plug in the n, the infinity for n, but there is no n, so I just get the absolute value of x minus 2 over 2 has to be less than 1. Okay, to drop the absolute value signs, we will have to write this as the absolute value, or x minus 2 over 2 has to be less than 1, but greater than negative 1. Okay, now we solve for x, so I'm going to multiply both sides by 2, multiply by 2, and, well, I'm going to multiply everything by 2. I'm just going to write it like this, times 2. Okay, so I get negative 2 is less than x minus 2 is less than positive 2. Okay, and then I need to add 2 everywhere. Okay, so I have 0 is less than x, which is less than 4. On my number line, I can now see that I am centered. My C value is equal to 2. So I'm going to put 2 in the middle. And then I have a radius. So my interval of convergence is going to be from 0 to 4. Okay. So I know that everything here, all the values, if I plug in like 1, 1.5, negative 1, negative 1 point, or no, not negative 1. So 0.1, if I plug in 0.1, 0.5, 2, 2.1, 3.99999, those will all converge, but I'm not sure yet about the endpoints, about 0 and 4. Before we do that, I do need to write that the radius is equal to 2 because we are 2 units in both directions from center gives us our endpoints, okay? So the radius is 2. I can say that the center is equal to 2 as well. That's the center is equal to 2. The radius is equal to 2, okay? All right, so to figure out about the ends, we have to test the ends. So the way we do that is we substitute in the endpoint values into our series, and we just see if that value converges or not. So we just have to do them individually, okay? So I'm going to let x equal 0. I'm going to use my original series from all the way up here, okay? This guy right here. And I'm going to substitute in x. So I have the sum from n equals 0 to infinity of negative 1 to the n plus 1 times x minus 2 to the n over n times 2 to the n. And then what we're saying is, if I plug in 0 into this series, is the series going to be a good estimation of or good approximation of the series, okay, of the sum. So I plug in 0 for x. So n is equal to 0. The sum from n equals 0 to infinity of negative 1 to the n plus 1 times 0 minus 2 to the n over n times 2 to the n. Okay, well, now we need to simplify. So I have the sum from n is equal to 0 to infinity of negative 1 to the n plus 1. Okay, I know that 0 minus 2 is going to be negative 2. So I'm going to write this as negative 1 to the n times 2 to the n all over n times 2 to the n. We see that our 2 to the n's cancel. And, okay, n to the 1, n plus 1, negative 1 to the n plus 1, and negative 1 to the n. Okay, if I plug in 0 for n, 0 plus 1 would give me 1. So, and if I plug in 0 for n here, -1 to the 0 is equal to 1. So this would be +1 and a -1, right? Negative times a positive is going to give me a negative. Okay, now let's look at what if n is equal to 1. So if n is equal to 1, then 1 plus 1 would give me 2. And then this would be n to the 1. So -1 squared would be +1, and -1 to the 1 would be -1. So you can see that always we're going to have one of those -1 terms is going to equal a -1, and one is going to equal a +1. So together, these are just going to make -1. So I'm going to have the sum from n is equal to 0 to infinity of -1 over n, because one is always positive and one is always negative. Okay. All right. So what we're figuring out then is the sum from from 0 to infinity of -1 over n. And what we have is, I can just rewrite this as negative -1. Yeah, so I can write this as negative, so I can bring the negative in front. Just had a moment there. Of 1 over n. And so 1 over n is p is equal to 1, so the series diverges. What we're going to end up is basically negative infinity. So the series diverges by p series test. Okay, so when I go back to my radius of my interval of convergence, I need to write a parentheses at 0 because that point is not included in our interval of convergence. Okay. All right, so we're halfway there. We're going to do the right endpoint now. So we're going to let x equal 4. Okay, so we have the sum from n is equal to 0 to infinity of -1 to the n plus 1 times x minus 2. So we're going to plug in 4 for x. So 4 minus 2 to the n over n times 2 to the n. The sum from n is equal to 0 to infinity of -1 to the n plus 1 times 2 to the n over n times 2 to the n. We get some canceling. Got to get canceling. Okay. So I end up with the sum from n is equal to 0 to infinity of -1 to the n plus 1 over n. So the numerator says that this is going to be an alternating series. So as the degree becomes even or odd, we'll have a positive and a negative, positive and a negative. So I'll use the alternating series test. So I'm going to take the limit as n approaches infinity of 1 over n, which equals 0. So that's the first condition. The second condition is that 1 over n plus 1 has to be compared to 1 over n. The denominator is larger, so it's going to be smaller. So that means this function decreases. The absolute values of the terms decrease as x increases. So the series converges by alternating series test. Okay. So when I go back to my interval of convergence, I would put a parentheses because the value x equals 4 can be included in our interval of convergence. So the last thing we have to do is just write out our interval of convergence. I'm going to write it as 0, comma 4, or 0 is less than x, which is less than or equal to 4. Okay, so the radius is r is equal to 2, and here's our interval of convergence. Okay, we're going to do one more here. These take a while because you have to test both endpoints and use the ratio test. All right, so I have the sum from n is equal to 0 to infinity of x minus 3 to the n plus 1 over n plus 1 times 4 to the n plus 2. In the x term, I can see that we are off by -3, so that means that the center is going to be around 3. Okay, so we're going to need to add or subtract from our center of 3. Okay. All right, so I wrote something weird on my paper. Okay, I have the limit as n approaches infinity. We're going to apply the ratio test. So x minus 3 to the n plus 1 is 2 over n plus 1, so n plus 2 times 4 to the n plus 2 times the reciprocal of a sub n, so n plus 1 times 4 to the n plus 1 over x minus 3 to the n plus 1. And we need this to be less than 1 to figure out where we converge. All right, limit as n approaches infinity of x minus 3 to the n times x minus 3 to the 2 over n plus 2 is fine. Then we have 4 to the n times 4 squared. So times n plus 1 stays, and then we get 4 to the n times 4 to the 1 over x minus 3 to the n times x minus 3 to the 1. And all of this needs to be less than 1. Okay, I got the limit as n approaches infinity of, okay, let's cancel. That cancels. 1 factor of x minus 3 cancels. 4 to the n's cancel, and then 1 factor of 4 cancels. So I have x minus 3 times n plus 1 all over n plus 2 is, do I have a factor of 4? No, okay, is less than, oh, I forgot a factor of 4. In the denominator, there was an extra factor of 4, so I need to make sure I multiply by that as well. Okie dokie, okie dokie. All right, so I'm plugging in infinity in for n, so I'm going to end up with infinity over infinity is less than 1, but we need to apply L'Hopital. Or you can just say, this is a eats DC situation, so I'm going to divide the coefficients, which are x minus 3 over 4. Okay, so either way it works. I'll take the long way. Okay, so I'm going to take the limit. The derivative of n plus 1 is 1, so I get x minus 3 over 4 because the derivative of n plus 2 is 1. Okay, and this needs to be less than 1. There is no n to plug in, so I'm just going to end up with the absolute value of x minus 3 over 4 has to be less than 1. Look, if you just go back and look, okay, we knew that these terms are going to cancel, so we're going to end up with x minus 3 over 4. We're dividing the coefficients. Whoop, the long way. Okay, x minus 3 over 4 has to be less than 1, but greater than -1. We're going to multiply both sides by 4, or all sides by 4, so we get -4 is less than x minus 3, which is less than 4. Then we're going to add 3 everywhere. Why not just write it? Okay, so I get -1 is less than x, which is less than 7. When I draw this on my number line, I know that my center was 3, and then I'm basically one of my endpoints is 7 and the other one is -1, so I can see that the radius is equal to 4. So I'm 4 units away from my center in the positive direction and the negative direction. Okay, so that's first, the radius of convergence is 4. Now we need to figure out what our interval is going to be. The interval, we have to test the endpoints because we're not sure if the endpoints converge or not. So we need to let x equal -1 first, and then we're going to let x equal 7. So we plug this into our original series. So n is equal to 0. The sum from n is equal to 0 to infinity of the original was x minus 3 to the n plus 1 over n plus 1 times 4 to the n plus 1. Okay, let's jam. Here we go. The sum from n is equal to 0 to infinity of, we're plugging in -1 in for x, so -1 minus 3 to the n plus 1 over n plus 1 times 4 to the n plus 1. Okay. So a lot of writing. -4 to the n plus 1. I can understand if you can write one less step here or there. Okay. So this is what I have so far. I'm going to rewrite this numerator as -1 to the n plus 1 times 4 to the n plus 1 over n plus 1 times 4 to the n plus 1. And then we can see that the 4 to the n plus 1s are going to cancel. And so I'm just looking at the sum from the sum of -1 to the n plus 1. So that looks like alternating over n plus 1. So since this is alternating, let's go ahead and use the alternating series test. So the limit as n approaches infinity of 1 over n plus 1 is equal to 0. Okay, that's the first condition of alternating series. The second condition is that our term of 1 over n plus 1 has to be greater than the next term. So in other words, each term the absolute value of each term has to decrease. So yes, this is going to the terms are going to decrease over time. Okay, so this series converges by alternating series test. So when I go back to my interval of convergence, I am going to draw this is my interval. I'm going to draw my bracket there, and then I'm going to go ahead and test the second endpoint. So we're going to let x equal 7. The sum from n is equal to 0 to infinity of x minus 3 to the n plus 1 over n plus 1 times 4 to the n plus 1. We are replacing the x with 7. So I'm going to put 7 minus 3. So that's 4 to the n plus 1. I drew that sum really weird. Times n plus 1 over n plus 1 times 4 to the n plus 1. And these cancel to give me the sum from terms n equals 0 to infinity of 1 over n plus 1. All right, so what are we going to use here? Well, you have a lot of options. So I tried first to use direct comparison tests because I was like, oh, 1 over n is greater than 1 over n plus 1. And I drew it because it helps me. So if I'm like 1 over n, and 1 over n plus 1. I know this one diverges so that it really doesn't tell me anything about the bottom series because it's lower. So I don't know if it's going to diverge or converge. Okay, so I don't know. Let's use the integral test. So I have for integral test, if the function is 1 over x plus 1, it has to be positive. The outputs have to be positive, continuous, and decreasing. And we're good there. Okay, it's positive, continuous, and decreasing. So we're going to take the integral from 0 to infinity of 1 over x plus 1 dx. And so I need to rewrite that as the limit as b approaches infinity of 0 to b of 1 over x plus 1 dx. Okay, so I take the limit as b approaches infinity of the ln of the inside, so the absolute value of x plus 1, divided by the derivative of the inside, which is just 1. Okay, so from 0 to b. So I have the limit as b approaches infinity of the ln of the absolute value of b plus 1 minus the ln of 1. Okay, so we end up with infinity minus 0. So the series diverges by integral test. Could you use a different test? Absolutely. Okay. So I'm going to go back to my number line and I'm just going to write a parentheses. So I know that my interval of convergence would be from included is -1 to 7 excluded. Okay. Or -1 is less than or equal to x, which is less than 7. Okay, that was a lot, but we are done for now.